Hello, my name is Kyungmin Kim, and I'm here to introduce what the deep neural network is. So deep neural network is nothing but the nonlinear regression estimation method, which assumes the structure of that regression function with the multiple layers of nonlinear factor models. So what we've got to first know is what the linear factor model looks like, as we have learned in the multivariate statistics class in the undergraduate level statistics courses. So linear factor model. I've put the word linear in front of the factor model in order to discriminate this modeling technique with the nonlinear factor modeling cases. So as we have seen in undergraduate level regression analysis class, capital X is usually used to express the design matrix of order n by p. So in each row, there is an observation of p covariates. And in linear factor model, we consider its transpose. So X transpose, which is of size p by n. And we can express it as a affine transformation using the factor variables as follows. So there exists a weight matrix W, which is of order P by Q. Let's say there are Q factors. So it is a transformation from the Q space, RQ space to RP space. And we usually use the notation capital F. But since we're talking about the deep neural network structure, let's say a matrix A of size Q by N. So each column contains the factor variable values for each observation and plus the bias vector of size p by 1. So one might ask, how can we add the matrix and the vector? Simply think this vector can be understood as a matrix of rank 1 whose column is B respectively. So this is the linear factor modeling technique. And as we assume in the factor analysis, let's say that the design matrix X is pre-centered. It's centered before we do the analysis, factor analysis, let's say. So it's simply just expressing the p covariates as a linear combination. More accurately speaking, a fine transformation of the Q factors. But this is all about the linear factor model. Let's don't think about how to estimate these weight matrix W right now. And second, let's think of the nonlinear factor model. Nonlinear factor model is nothing but taking the activation function, which is often denoted as the Greek letter sigma, to the affine transformation WA plus B. So let's assume that this sigma function, activation function, is a nonlinear function of the factors A. Then this is the nonlinear factor modeling. If it's a linear transformation, we can understand it as a linear factor modeling. Just think of the multiplication of two matrices, sigma and W, as a single linear transformation. Then it's nothing but the linear factor model. However, if we take the nonlinear transformation, then it becomes a nonlinear factor modeling. Generalized linear model can be understood as a kind of nonlinear factor model if the link function is nonlinear. So let's think of the GLM case. And the response variable is univariate, then xt can be understood as a 1 by n matrix of conditional mean. Conditional mean. And the nonlinear activation function sigma can be understood as an inverse function of the link function that we have learned in GLM in categorical data analysis class. And WA plus B can be understood as a linear predictor. It is simply a linear predictor. And each column of a matrix can be understood as the covariate values of the ith observation. So GLM can be understood as a kind of nonlinear factor model. And let's think of the final one. The final one is the deep neural network structure. It is nothing but a sequence of multiple nonlinear factor model as described in this second case. So if we take the conclusion first using the matrix A, we take the affine transformation first. It is a factor modeling, and then take the nonlinear activation function. Then it's a nonlinear factor model, and we understand this as another initial factor matrix, and we can take another affine transformation as follows and take another nonlinear transformation using the nonlinear activation function. Then this can be understood as deep neural network structure with a single hidden layer. And if we take multiple times the number of hidden layers will increase. And analogous to the second case, third case can be understood as a nonlinear regression problem. Let's think of this X transpose matrix is again a 1 by n matrix of the conditional mean of the univariate, in this case, response variable. Then using the deep neural network structure, which is obviously nonlinear, we're modeling the conditional mean. So we're assuming that the functional relationship between the conditional mean and the covariates are nonlinear, and to be more specific, it takes the structure of the deep neural network structure. So in conclusion, deep neural network is nothing but one of the regression modeling technique used for representing the functional relationship between the conditional mean and the covariates. So of course, if the response variable has an obvious linear relationship between covariates, then we don't need to use these complicated structures. And last thing to note, one of the key points that most of the people have difficulty in understanding the deep neural network is how to estimate these weights W's and biases B. So these are simply the regression coefficients, since it is a regression problem. So let's think of the ordinary least squares method. We just take the partial derivatives with respect to respective regression coefficients. Then we get the estimated regression coefficients. Let's think of the generalized linear model technique. What we do is to use the numerical techniques such as the Newton-Raphson method until certain conditions meet. However, as you can expect in this structure of the regression function, we have tons and tons of numbers of parameters to estimate. So simply taking the partial derivative, it may be inefficient in the estimation of the regression coefficients, weights, and biases. They're the same thing. So there comes the backpropagation technique. We use the gradient descent method sequentially as we take the Newton-Raphson method sequentially in the GLM case. And I'll explain the backpropagation method, how it works using the matrix notation next time. So this is all about the explanation of the deep neural network. I may not be mathematically or statistically rigorous. I'm just explaining you guys how I've understood the deep neural network in the context of linear algebra and the statistics that I've learned in undergraduate level. Thank you for listening.